TransPedia Research Talk Series organized by KSCSTE National Planning Research Center NATPAC. This talk series is yet another unique venture of NATPAC designed to explore diverse topics from cutting-edge technologies to sustainable solutions. Here, we will be featuring eminent young researchers to share their valuable insights for kindling the spirit of future research and development in transportation. Today, we have with us Dr. Anupam BR, Assistant Professor, Department of Civil Engineering, National Institute of Technology, Karnataka, Surathkal, for sharing his valuable insights on the topic Cooling the Concrete Jungle, Impact of Payments on Near-Surface Air Temperature and Mitigation Methods. Now, I request Dr. Shalini Yu, Senior Scientist, to deliver the welcome address.
Thank you, Rishma. Good morning, all. KSCSTE-NATPAC has been conducting the TransPedia Talk Series, a technical discussion platform aimed at fostering research for mutual benefits by sharing knowledge on diverse topics ranging from cutting-edge technologies to sustainable solutions since 2023. This initiative also creates opportunities for young researchers worldwide to connect and collaborate, shaping the future of research and development in transportation. Over the past 2.5 years, around 29 sessions have been successfully conducted, covering a wide array of topics in transportation engineering. Today marks the 8th talk in the series, which will be delivered by Dr. Anupam BR, Assistant Professor, Department of Civil Engineering, National Institute of Technology, Karnataka, Surathkal. It is an honor and privilege to welcome the esteemed speaker who will share his expertise on the topic Cooling the Concrete Jungle, Impact of Payments on Near-Surface Air Temperature and Mitigation Methods. Following the presentation, there will be a question and answer session offering you the opportunity to engage directly with Dr. Anupam. We encourage your active participation in this meaningful exchange of ideas. Thank you once again for joining us. Please be in extending a warm welcome to Dr. Anupam as we look forward to the session. Thank you.
Thank you, ma'am, for your welcome note. Now, I would like to invite Dr. Gautam Sarang, Junior Scientist, to introduce the speaker to the audience.
Thank you. Good morning, everyone. It's my pleasure to introduce today's speaker, Dr. Anupam BR, who is currently serving as Assistant Professor in the Civil Engineering Department at NITK Surathkal, Karnataka. Dr. Anupam holds a PhD in Civil Engineering from IIT Bhubaneswar, where his research focused on advanced and sustainable payment technologies. He completed his MTech in Transportation Systems Engineering from NIT Hamirpur and his BTech in Civil Engineering from MG University, Kottayam. He has also worked as a postdoctoral fellow at IIT Bombay, gaining strong exposure to cutting-edge research in geopolymer concrete and recycled fiber reinforced pavements. His research interests include cool payments, geopolymer concrete payments, roller compacted concrete payments, use of waste materials in payments, and quiet payment technologies, all of which are highly relevant to sustainable and climate resilient infrastructure development. Dr. Anupam has an impressive publication record with more than 25 papers in reputed international journals including Construction Building Materials, ASC Journal of Materials and Civil Engineering, International Journal of Payment Engineering, etc., and in many national and international conferences. His work has contributed significantly to payment thermoregulation, urban heat island mitigation, and sustainable materials. In addition, he actively contributes as a reviewer for leading journals such as Construction and Building Materials, Journal of Materials and Civil Engineering, etc. With a strong blend of academic rigor, practical research, and service to the profession, we are fortunate to have Dr. Anupam with us today. So please join me in warmly welcoming Dr. Anupam BR for the 30th TransPedia talk. Thank you.
Thank you, sir, for the introduction. Now I invite our distinguished speaker to deliver the talk. Over to you, sir.
Thank you for the warm welcome and also thank you for inviting me to this event. Exactly how much time do I have? 45 minutes or 30?
You can take 45 minutes, then we'll have around 10 to 15 minutes of Q&A session.
Okay, thank you. I will share my slide. Hope my slides are visible now.
Yeah, you may make it full screen. Yeah, yes. Please proceed.
Thank you. Good morning, all. Thank you for inviting me, as I already said. Today, I'm going to present a small session on cooling the concrete jungle, impact of payments on near surface air temperature, and mitigation method. So, I'm currently, as introduced, I'm working as an assistant professor at Department of Civil Engineering and ITK, Surathkal. So, this is a brief about my research group, Sustainable and Resilient Payment Research Group. It currently has one PhD scholar and some PG students, and we mainly work on payment material characterization, design and construction of payments, repair, maintenance, and rehabilitation of payments, and next generation payment technologies like pool payments, quiet payments, self-healing payments, and utilization of waste materials in payments. So, coming to today's talk, I'll be giving you an introduction about urban heat island, interaction between payments and urban heat island, and pool payments. After that, I'll be sharing some ideas about my ongoing research, which is conducted here as well as partially at my parent institute or my PhD institute, IIT Bhubaneswar. So it is a mix of both. So I'll give you a brief methodology and the ongoing outcomes or partial outcomes yet to be published. So coming to urban heat island. Urban heat island is a phenomenon of higher air temperature experienced by an urban area than that of its surrounding rural area. For example, if the rural temperature is 30 degrees and the city temperature is 40 degrees Celsius, that difference, or we'll say that city is 10 degrees Celsius hotter than its surrounding area, or the urban heat island intensity of that city is 10 degrees Celsius. Many cities around the globe and most of the Indian cities are also experiencing this phenomenon. Because city is hotter than this, its surrounding means incoming solar radiation is almost same, but due to some artificial structures or artificial materials which is present in the city, which is not present in the surrounding, is storing heat and heating the city. So that cannot be excluded. Means if that is avoidable if we plan the city properly. Means up to 10 degrees Celsius reduction in the temperature means significant energy can be reduced in terms of AC load. Cooling efficiency or cooling load will decrease. This will reduce the energy load as well as emissions related to that, all those issues. So urban heat island is a bad or harmful phenomena to the cities, and most of the Indian cities are now facing this problem. Not only Indian cities, global cities are also facing. So the main causes of urban heat island is low albedo materials like our black asphalt pavements. They are continuously exposed to solar radiation, so heat absorption of that pavements, air pollution, these pollutants present in the air will absorb more heat, wind blocking due to the tall buildings, deforestation, air conditioner which absorbs a load or cool means which will emit heat outside the building, human activities like vehicular traffic which emits carbon dioxide. All those things contribute to elevated city temperature and urban heat island effect. This urban heat island effect has harmful impact. For example, if you see the statistics from Japan, a steady increase in heat-related death was reported or heat-related illness was reported from the past years with increase in temperature. And when there was a heat wave in 2010, this heat-related death was at the peak. So there are evidences from different countries that increasing or elevated temperature lead to health issues and sometimes death also. It has environment impacts like higher emissions, decreased air quality, water quality, local wildlife like wildfire, and everything. It adversely affects the health and well-being of the citizens, and also it has economic and infrastructure impacts also. So as a whole, this is a phenomena that we want to or we should be tackling or we should be mitigating. So payments contribute to urban heat island because payments cover about almost if you consider a city around 30 to 40% by area. If you see the top view, 30 to 40% of the urban area is payments. And evidence from Bhubaneswar city shows that about 60 to 70% of the temperature rise of the city from 2004 to 2015. The cause is variation in land use and land cover. Means if you take the case of Bhubaneswar city, up to 70% of temperature rise experienced by the city in past 10 years is due to the change in natural vegetation to artificial structures, both asphalt as well as concrete and buildings. And that's mainly because the heating index of these materials is much, much higher than natural materials like sand and grass. It heats the surroundings much more than not natural materials. If you see the thermal image of an urban street, it reaches up to 61 degrees Celsius, means the temperature of the asphalt pavement surface can reach up to 61 degrees Celsius. And this higher asphalt pavement heats the surrounding air also, which is one cause that leads to urban heat island effect. Cool pavements is a technology which is mainly invented to reduce the impact of pavements on this phenomena. Means these pavements are specially designed so that its temperature will not rise up to 60 degrees or 65 degrees Celsius, or it will remain cooler than our normal pavements that we are currently using. So this is the United States Environmental Protection Agency definition for cool pavements. It's a range of emerging technologies that communities are exploring as a part of their heat island mitigation effort. This term currently refers to paving materials that reflect more solar energy, enhance water evaporation, or have been otherwise modified to remain cooler than conventional pavement. Means its temperature under solar radiation, these pavements will be cooler compared to other normal pavements or compared to the conventional pavements that we are currently using. So there are three types of pavement, cool pavements mainly: reflective pavements, evaporative pavements, and heat storage modified pavements. Reflective pavements, as the name indicates, they are lighter colored pavements. Usually we might have heard about the blue roads of Qatar. Instead of black, it will be some lighter color, but not white. White, we will be having visibility issues, but lighter than black. Evaporative pavements are porous pavements which holds water in the pores, so that water will take the heat and evaporate, so the pavements will not be heated much. Porous parking lot of Gandhinagar railway station is an example of this type of pavement that we have in India. Heat storage modified pavements are novel technologies like high conductive pavements, energy harvesting pavements, and PCM incorporated pavements. We'll be discussing this in coming slides. So these are new technologies or emerging technologies with a lot of research and innovation potential yet to be applied in large scale in site. So reflective pavements, as I indicate, they are lighter colored pavements. So somehow, if we can, instead of black, if we can apply some coating like reflective coating or some coating which reflect only the infrared rays, or some thermochromic coating, or somehow if we are able to make the pavement lighter colored, then it already conventional pavements are. Basic physics, the incoming solar radiation will be reflected. So due to reflection, the heat energy absorbed by the pavement is less. That will reduce the pavement temperature. That types of pavements are known as reflective pavements. But the problem is that this reflected radiation, if it is reflected to the atmosphere, then it is okay. Some cases, if there are nearby buildings to the pavement or pedestrians or vehicles traveling on that road, it will reflect to that material or that person or that building or that vehicle and cause harmful impact or thermal load, increase the thermal load of that building. So ultimately, pavements are just reflecting the radiation and remaining cooler. It is not contributing to the intended use like UHI mitigation. Just reflecting to the surroundings is not UHI mitigation. So this is not always suitable for every terrain. If the pavement is open or it has enough space at two sides so that reflected radiations will be gone to the atmosphere, then it is fine. But closed canopy, it is not suitable. So it is location specific. This is one of the major demerit of reflective pavement. So we have to invent new technologies. Evaporative pavements, they are pavements which are designed like porous pavements or pervious pavements, which will store water in the pores. And when the temperature increases, this water will absorb the heat from the material and evaporate. So since the heat energy is consumed by water for evaporation, pavement temperature will be less. Key issues of evaporative pavements are, in the absence of water, these pavements will be hotter than our normal pavements. So when there is water, it is okay. It will be cooler, evaporation things will happen. But in the absence of water, this mechanism will not be there and payments will behave hotter than that of our normal payments. And in countries like India and somewhere where water is availability is a problem, these payments cannot be used. It is only suitable or it is only working in the presence of water. If water is not there, temperature will increase and it is hotter than that of our normal payment. So the third category of technology was invented to avoid these demerits, and first among that was energy harvesting payments. Energy harvesting payments are that will absorb or somehow absorb and convert the heat energy to some other source of energy. We have solar roads, like we will be laying basically or literally we'll be laying solar panels on the roads, and the solar panels will be converting the heat energy into electrical energy. Or we have geothermal or hydronic payments in which we'll be laying pipes below the payments, and this water will be circulated through these pipes, and this heat energy will be absorbed by this water and water will be heated, and that hot water can be used for some other purpose. Basically in cold climate or cold countries, these two are already applied technologies also, not even in research stage. This first one is the pipes, that orange color that you see is the pipe being laid below the pavements, and you lay the asphalt over that and compact it and like a smooth as usual. Water will be circulated through that orange pipe that you can see in the left side. When water is circulating, water will absorb the heat from the asphalt and it will be carried away. So the pavement will remain cooler, but plus extra benefit is you will get hot water, and this hot water can be used for some other purpose. The right side, you can see the solar roads of China. It is a 1 kilometer road. You can see the solar panels and it is able to carry heavy traffic also. You can see the trucks are going, and what they have did is they have laid the solar panels over that. To protect that, they have laid a concrete which is transparent. They laid the solar panel, they laid a transparent concrete. Transparent concrete, they use glass as aggregate, 100% glass aggregate, and some polymer or some chemical as binder. Transparent aggregate and transparent binder, they laid over the concrete or laid over the solar panel so that the solar panel is protected. Even if vehicle moves over that also, this solar panel is protected, as well as since it is transparent, it is working properly. Next one is PCM incorporated payments. Phase change materials are materials that changes its phase, like ice. Ice changes its phase from ice to water, water to ice at 0 degrees Celsius. So 0 degrees Celsius, we can say that it is the phase change temperature of ice. Like that, we have different materials which changes its phase at different temperatures. Like 30 degrees Celsius, 40 degrees Celsius. Ice it is 0, but wax, if you see candle wax, it may be at 50 degrees Celsius or something. So there are different materials. So suppose you have a material that changes its phase at 45 degrees Celsius. So below 45, it will be in solid state. Above 45, it will be in liquid state. And somehow you imagine that you are adding this solid PCM at 40 degrees Celsius into the pavement, into our normal roads. And when the temperature of the pavement increases, this material will start melting. At 45 degrees Celsius, this material will start melting. Melting means this material will start absorbing heat from the pavement and changes its phase from solid form to liquid form. So for that conversion, solid to liquid conversion, heat energy is required. It is taking the heat energy from the pavement. So heat energy from the pavement is consumed, means since heat energy is consumed, heat of the pavement or the temperature of the pavement will not increase. So that as far as the process is going on, temperature of the pavement will not rise. So assume that pavement, this phase change process is continuously going on and sunset happens, so that the pavement temperature is ideally restricted to 45 degrees Celsius, because this above that the pavement, this material will be absorbing heat and melting. So if we add this, we can regulate the pavement temperature. That is the idea. So we have, since we cannot directly add this material into the pavement because when it melts, it will flow away. So we are adding it in encapsulated form. You can add it inside some material like lightweight aggregate or something, and you can add that material into the pavement. So today we'll be discussing about high conductive payments, my research related to that. So high conductive payments are also a kind of technology. We'll just add some high thermal conductivity material like some metallic things or graphene or graphite into the payment so that its thermal conductivity will be increased. So when the thermal conductivity of the material is increased, when heat reaches the surface, it will be transferred to the bottom layers at higher rate because higher thermal conductivity means rate of heat transfer is high. So it will transfer the heat from the top to the bottom at a higher rate. So heat will reach the bottom layers, subbase or subgrade layers at a faster rate. So top will be cooler and more heat is reaching at the bottom layer. Bottom layers will be more hot. But in the bottom layers, moisture will be present. So this moisture will take that heat and evaporate. So since moisture is present at the substrate, this moisture will take care of the heat and evaporate. So ultimately, this heat transfer happens, and transferred heat at the bottom layers are taken care by the moisture present in the bottom layers. This will ultimately lead to a high conductive payment system. So ongoing research and key findings basically related to payment and air interaction as well as high conductive payments, some numerical research related to the high conductive payments I'll be presenting today. So coming to the methodology to analyze the impact of payments on air temperature, this work was done as a part of my PhD work at IIT Bhubaneswar. So Bhubaneswar was selected as a study area. We conducted vehicular surveys through the Bhubaneswar city. We crossed the city from the rural area, go to the city center, again went to the rural area in two cross directions. And at intermediate points, we took the temperature and humidity reading as well as the payment temperature reading. So temperature we measured at just near to the surface at different heights. At 1 meter height above the pavement, what is the temperature? 1.5 meter height, what is the temperature? Like that. So the aim was to quantify the urban heat island intensity of Bhubaneswar city physically through measurements, as well as also to establish a relationship between pavement temperature and air temperature. If the pavement temperature is this much, how much is the air temperature, or to quantify up to what height or what is the area that the payment is having an impact due to its temperature variation. After that, we tried to develop a numerical model related to the high conductive asphalt payments. This is what happens. So that red line is the incoming solar radiation. So this is the incoming solar radiation. So if Q is coming, due to the solar reflections, a part will be reflected and remaining will be gone into the pavement. There will be, of course, radiation and convection due to wind. So these are the cooling parameters. But incoming solar radiation is taken by conduction. There will be heat transferred to the pavement, and this conduction part is ultimately heating the pavement. So we developed a two-dimensional bituminous pavement system as shown in this figure. Two sides are assumed as insulated and constant temperature at a deep 3-meter pavement layer, which is experimentally also proven. And this was the layer thickness assumed. And we assumed that a Q amount of heat is coming and a part is reflected, and radiation and convection properties are also there. And a part is going to the pavement down. A two-dimensional model was developed in Fortran coding language. And for various thermal conductivity, we change the conductivity of this material in the range that we can achieve by adding some materials. And we see how the temperature of these materials are, or under solar radiation on a typical day, how is the pavement surface temperature varying? Means if we increase the thermal conductivity, are we really achieving the reduction in pavement temperature? That also we have done. And we have validated the model using experimental results. We casted asphalt pavement test slabs as exact dimensions that we considered in the model, and we collected data, experimental data using thermocouples and data logger system. And we validated the model. We validated our data with experimental and numerical model. So coming to the results, this was the urban heat island intensity results as a result of the vehicular surveys that we have conducted in the Bhubaneswar city. You can see the temperature of the Bhubaneswar city, or the intensity of Bhubaneswar city, UHI intensity of Bhubaneswar city was around 1.8 degrees Celsius. Means the city was around up to almost around 2 degrees Celsius hotter than its surrounding area on that particular day. I am not generalizing this. We conducted the survey on some days. So taking an average on that day or on an average on that range, this was urban heat island intensity, and its intensity varies. Today it may be 2 degree, tomorrow it may be 3 degree. To quantify it, we need a huge data, maybe for a 1 year or 5 year period, we can average and say this is the intensity of the city. For a short period of time, I conducted the survey. The city was up to 2 degrees Celsius hotter than its surrounding rural area. And you can also see that as we move towards the city, to the city center, as you can see in both routes, at the city center, more hot. And if you approach the rural areas, temperature will get reduced. So maximum heat intensity or maximum urban heat island intensity is experienced by the city center, maybe due to the high concentration of buildings or more vehicular traffic or industry activities, maybe because of that. And quantifying the impact of payments on air temperature, I measured the payment temperature at different heights from the payment at different location, and I managed to fit a curve, or I managed to find a relationship between payment temperature and air temperature. As you can see, maybe visible from this diagram, up to 1.5 meter height, payment temperature was having an impact on the air temperature. Above that, above 1.5, whatever changes in payment, or the changes in payment temperature was not affecting the air temperature. Or I can say closer to the payment, up to a height of 1.5 meter. If the payment temperature increases, the air temperature up to 1.5 meter height also increases. Above that, this impact was not direct. I'm not saying payments do not have any impact, but this impact was not direct. It's not having any direct impact. So this was a result of model validation. As you can see, this experimental data and numerical data are well correlated. Our score was around 96.96, up to 96% variation in the experimental can be determined or can be explained by the model also. So I did, or from a morning 6 a.m. to evening 5 a.m. or the next day morning 5 a.m. I tried to simulate a curve how this payment surface temperature varies with different thermal conductivity. These ones are the variation in thermal conductivity. As you can see, when the thermal conductivity increases, the payment temperature decreases. Peak reduction was reported during the noon time. You can see the curve. This blue line is least thermal conductivity, 0.5, and this orange line is higher thermal conductivity, 2.5. So there is up to 10 degrees Celsius reduction, but maybe this 2.5 may not be practically possible, but still I have considered normally, but you can achieve this green line 1 higher or 1.5 very easily. So this is a maximum payment surface temperature. You can see while the maximum payment temperature surface temperature is 63 degrees Celsius, with 1.5 itself, you can reduce up to 5 degrees Celsius temperature. So peak payment temperature surface temperature is reduced when you increase the payment thermal conductivity. Temperature reduction or cooling potential is increasing. And as you can see, this is a temperature gradient diagram that I have obtained using the plot. You can see that the temperature gradient means the top difference between top surface and bottom surface is also getting reduced as we increase the thermal conductivity of payment, or we can say a more homogeneous thermal temperature distribution over the cross section of the payment. And this is how it varies with time. You can see that always the peak reduction is observed during the noon time, or which is the main intention. When the payment temperature is at peak, the maximum reduction should happen. We don't have to reduce the payment temperature during early mornings or late night. We are targeting the maximum reduction during the peak hours. So it is happening, as you can see here. And as you can see, the temperature is more homogeneously distributed, or the variation in payment temperature is more homogeneously distributed, or it is less, or the temperature is homogeneous as we increase the thermal conductivity of the system. So different representations of the same results. So coming to the conclusions, we can like to conclude with these preliminary results that payments have an impact on the air temperature, or payments heat the surrounding air temperature, and it has an impact up to 1.5 meter above the payments. And increasing the thermal conductivity can reduce the temperature of the pavement, and deeper heat penetration happens due to higher thermal conductivity as we expect, and diurnal variations in the temperature is also less, means less fluctuations. It's not like higher pavement temperature during daytime and least pavement temperature during nighttime. That fluctuation is also getting reduced, which is also good. And also the peak pavement temperature reported, like 60 is reduced to 59, 53, like that. The maximum pavement temperature reported is also getting reduced, as well as the temperature is also getting reduced. Means there is a cooling effect also. So these are the references. With this, I would like to end my presentation. If you have any queries, you are most welcome. Thank you.
That was an informative session. Thank you, sir. Now the forum is open for discussion.
This is Shalini from NATPAC. It
Yeah.
was really a wonderful session. I just had a few doubts. In the model which you had shown, where did you place the thermal conductivity or that material, like in the BCDB
Only
base
the
subgrade?
only the top layer, means top bituminous concrete and DBM layer. Only the asphalt layer. I assume that entire bituminous layer we are adding the thermal conductivity material.
So it is within the layer or on the surface?
Actually, within the layer, inside the layer. And means practically when we are constructing this bituminous layer, we have to mix this material with the mix. Either we can modify the bitumen used for that, graphene modified bitumen or graphite modified bitumen, or we can add some materials. For example, steel slag, we can use steel slag, which is having higher thermal conductivity than normal aggregate. Such materials we can use, means it is during the mixing stage. We have to add higher conductivity material during the mixing stage, or into the binders, means we have to modify the binder with higher thermal conductivity material and use that material for the construction purpose.
Okay, thank you. One more doubt. Did you take the readings of daily? I mean, like you showed the hourly readings, right? But summer, what about the seasonal variation?
Actually, this data is just for one day. That is simulated data. I have readings for more also, means this is just not directly taken data. This is the results that I got from the modeling. So this is just for one summer day. I have simulations up to 1 week and different seasons also. Actually, we have, I have not presented here. During this experiment, we have collected data continuously for 1 year, both because this setup is powered by solar radiation. We installed this. So one payment made of without cooling technology, and 2 other sessions which are cooling. So all the 3 payments, we have collected data continuously 24/7, day and night, up to 1 year. So entire 1 year data was experimentally collected, and statistical analysis was done. And all this data you can see in one of my publications. I can share you if you are interested, because it's that data is the seasonal variation data. I have not presented it here.
So one more thing, rainy season, will they have some effect on this?
Yes. Rainy season, the temperature observed is less. Means both normal payments and this cool payment temperature observed is less. Basically, most of the cooling, we aim to this cooling action to be come into place when the payment temperature is higher. For example, most of the technologies are designed like when the payment temperature is above 40 degrees Celsius, they should be coming to action. At lower temperature, suppose the temperature of the payment is 30 degrees Celsius, we don't have a problem. So we assume that cool payments can also at 30 degree or 35 degrees Celsius. Cool payments do not, means they should not be acting, or no need of that cooling action. So we design, if we are designing any cool payment technology, we design like if the temperature is 60 degrees Celsius, this cooling should be in action. At 30 degree or 35 degrees Celsius, we don't want that cooling action. So we assume that, or we are not designing it for that. So during the rainy season, when the temperature is low or when it is raining, both will be reporting almost same temperature only, not much variation. Our aim is to reduce the hot temperature mainly during summer. So this action, cooling action, will be mainly coming into picture in summer only. In rainy season and winter, almost both will behave same. Very little variation will be there, but both will vary almost same temperature.
Thank you, sir. Actually, my question was like when the water permeates or when water affects the bituminous, will it affect the readings or will it affect the functioning of the thermoconductivity?
No. Thermal conductivity will not be, means that material will not be washed away. That's why we are adding it in construction phase. If you add graphene into bitumen, it will be blended into bitumen and bitumen will be graphene modified bitumen. So these additives will not be washed away. And also if water enters also, usually water should not enter, it will not affect the entire thermal conductivity of the system. And if water is there, if it affects the thermal conductivity also, it is not a problem because when water evaporates, thermal conductivity will come back to its initial value. During summer, there will not be water. So thermal conductivity will be high only. If water enters, thermal conductivity may reduce, but still water is there, cooling is not a problem because we don't want cooling in if water is present because water will do the cooling. So if water is present, it will alter, but in summer there will not be water. Water will be evaporated. So it will be working properly. And once water enters and water leaves, thermal conductivity will be restored. These materials will not be washed away.
Okay, sir. Thank you. Thank you so much.
Yeah, Dr. Anupam, this is Dr. Gautam from NATPAC. So it was a very nice presentation. So I have a few questions. One is actually when you conducted the survey in Bhubaneswar, like you considered only asphalt payments or whether you're having any concrete roads there or have you tried in concrete roads?
Actually, in the survey, we can only conduct in asphalt roads because majority of the roads were asphalt only, and we wanted the reading. We crossed the city from two sides, so that much extent of concrete roads are not available in Bhubaneswar city. Mostly the roads are of bituminous only, so the entirely survey was on bituminous roads only. But concrete payment will also have similar effect, but not verified yet.
I just want to see whether you have any comparison between them. That's right. No, right?
No data.
Okay. And next is actually, as you told, the mix, whatever you are suggesting is a conventional mix. It can be any mix like BC, SMA, DBM and all. The only thing difference is the material is changing. Either you are using a different aggregate or maybe you are modifying the bitumen. That's all, right?
Yes.
Okay. And next is actually you mentioned about evaporative payment. So there is basically a porous payment, right? Or it's a different one?
Porous payments, actually evaporative payments, we can say classify into four. I have not shown it here. Porous, permeable, pervious, and water retaining. So basically everything will be storing water. So this water storage or this permeability, water entering, some water will be stored. So after the rain, only for a few hours. If it is raining, suppose we get summer rains, water will be entering, and for maybe for that day only it can manage. Water will be evaporated and water will be gone. So in some countries they are watering in early mornings. They have constructed these payments, and in early morning they are watering this payment so that water will enter. By evening, cooling will happen. Evening, water will be completely gone. And again, they have to water. So only in the presence of water, this will happen.
And you mentioned like the porous payments are generally hotter than conventional payments.
In the absence of water, if there is no water, if in countries like India, if we construct it and if we are unable to water it daily, in the absence of water, this will be hotter. So porous payments will work only if water is there. So this is the cool payment payment only in the presence of water. If water is not there, I will not classify this as a cool payment because it will behave hotter. So that's why it is not suggested everywhere. Only if we are able to water it or water is available inside the payment, we can use. Else there is no point of using these kind of payments because this will behave hotter than our payments in the absence of water.
Okay, so you mean to say that it will be hotter than the conventional one?
It will be hotter than the conventional one. That is because if you go to the thermodynamics, we will say that the thermal mass is less. Means the heat energy stored To store that heat energy, the thermal mass available is less than impervious concrete. That's why in the absence of water, it is hotter. That's something related to thermodynamics.
Okay, thank you. Actually, we have our former director, Dr. Samson Matthew here.
Oh,
So, would you like to interact with Dr. Anupam?
Yes, sir. Hello, sir.
Hello, Anupam. Thank you, Gautam. So what happened, listen, I wanted to attend from the beginning, but in between I got a call, and that call, of course, it was last for almost 20 minutes, so I missed the the initial portion. But I found that one, it's a very, very interesting topic. And probably, we have to extend this one to the different the payment systems, and in general, it will affect the surroundings, habitations, and all. Anupam, I have a one because I didn't listen to your this presentation fully, but still, what will be the effect of that traffic on this on your studies? Whether
Yes.
because that also will give some effect on the the heat transfer and other things and all, no?
Yes, actually, personally, that effect was not considered in my analysis. Traffic will have two effects. One will be like if it is a densely traffic road with a dense traffic, this solar radiation will not be reaching the pavement. There will be shade of these vehicles, so it will be
Correct.
having a cooling effect. But due to this friction of tires, it will be having a heating effect. So that should be considered if you are considering the effect of traffic. Currently, in my analysis, it was not considered, or I can say mostly all of the pool payment studies, it is assumed that on an open area without traffic. In literature, also no studies are available. Like if it is a roads with more traffic, what will be the effect? But as far from my wild guess, it will have a very huge impact. High traffic volume roads, this solar or shading will be very high. Means sunlight will not be directly having a touch with the pavement, so it will be having extra cooling potential.
Okay.
That's what.
Good work, Anupam, and congratulations to you as well as your mentor, Sahu. Okay.
Yeah. Thank you, sir.
Okay. All the best. Okay.
Thank you.
Thank you, Gautam.
Thank you, sir.
Any other questions? Okay, if not, we'll wind up the session with.
I request Mr. Shidit Fifi, Junior Scientist, to propose the vote of thanks.
Yeah, thank you. Good morning, all. On behalf of KSCSTE-NATPAC, I would like to express my sincere gratitude to each one of you for joining the 30th TransPedia research talk on the topic, Cooling the Concrete Jungle, Impact of Payment on Near Surface Air Temperature and Mitigation Methods. So it has been a highly insightful and engaging session. At the outset, I would like to convey our sincere appreciation to our distinguished speaker, Dr. Anupam B.R., Assistant Professor, Department of Civil Engineering, National Institute of Technology, Karnataka, Surathkal, for delivering such an informative and thought-provoking presentations. Your detailed insight into the thermal behavior of payments, urban heat island effects, and the role of cooling payment technologies and mitigation strategies have been extremely valuable to our research community. So I also extend my heartfelt thanks to all the participants for your active participations. And special thanks to our former director Samson Matthew sir, and Dr. Sunitha from NIT Trichy, and many other external participants for your presence and interaction throughout the session. So once again, thank you, Dr. Anupam, for delivering such an excellent presentation. So furthermore, special thanks due to our director, division heads, and the TransPedia coordinating team at NATPAC for their continuous support and seamless effort to organize this event. So we look forward your participation in our upcoming TransPedia research talks. Thank you once again. Thank you all.
Thank you, sir.
Thank you for inviting me once again. Thank you for inviting me.
Participants, you may please leave the session.
Okay, thank you.